Hello friends! Continuing our training videos on the LS brand M100 inverter, today we want to learn about another feature of the M100 inverter. The feature we want to talk about today is the stop mode setting. In the M100 inverter, we have three types of stops. The first type is deceleration stop. The second type is stop after DC braking. And the third type is free run stop. Now, our first stop mode type is deceleration stop. What does that mean? If you set your stop mode settings to deceleration stop, the inverter, based on the maximum frequency you've set, will go from the maximum frequency to 0 Hertz within this duration. When you set the deceleration time, it begins to reduce the frequency and stops the inverter. For example, if you set parameter AD08, which relates to your stop mode, to 0, your stop mode will be via deceleration time. But where should you enter the deceleration time duration? In the main group of the M100 inverter, you can set this duration in the DEC parameter. For instance, if you set it to 5 seconds, the inverter goes from max frequency to 0 Hertz in 5 seconds. Meaning, as soon as you hit stop, the inverter divides the time between max frequency and 0, and your electric motor begins to come to a halt. So our first type was deceleration time, meaning the inverter, based on the deceleration time you specified, starts reducing frequency and stops your electric motor. Your second stop mode type is DC break-in. If we want, in certain applications, as soon as we issue the stop command, for our electric motor shaft to lock up and for our electric motor to stop instantly, we can do this through the DC braking stop mode. To have our stop mode on DC braking, we must set parameter AD08 to 1. But how does this feature actually work? The inverter, based on the rated current you entered in the motor parameters, induces a DC current into the electric motor winding, and the motor shaft locks, and your electric motor stops immediately. But the parameters you need to set in this stop mode, the first one is parameter AD14. In this parameter, you specify the time duration before applying the DC current to the motor windings. And parameter AD15, you specify the duration for injecting this DC current. For example, you set it to inject DC current into the motor windings for 3 seconds. In parameter AD16, you specify the DC brake level, meaning what percentage of the rated current you've specified should be converted to DC current and injected into the motor windings. And in parameter AD17, you specify the frequency related to the DC brake. For instance, if you have set parameter AD17 to 50 Hz, the inverter at 50 Hz and frequencies below 50 Hz, if you issue a stop command, the inverter immediately locks the motor shaft and your motor stops. But the last stop mode is free run. How does it work? Here, you no longer specify a duration. As soon as the inverter issues the stop command, your motor starts to stop based on the load inertia. The higher your load inertia is, the longer it takes to stop, and the lower your load inertia, the faster your motor will stop. So we learned that in the M100 inverter, we have three types of stop modes. The first was deceleration time, the second was DC brake, and the third was free run. Let's go to the M100 inverter and the settings we've made. Let's go to the M100 inverter, apply the settings we learned, and test this feature together. Okay, we said that in the M100 inverter, we have three types of stop modes. The first stop mode is via deceleration time. To set our stop mode to deceleration time, we go to parameter AD8 and set AD8 to 0. But where do we specify our deceleration time? In the main group, in the DEC parameter. Now, for example, I'll set it to 10 seconds. It scales these 10 seconds between the frequency of 60 and 0 Hertz. Now, if I give a command frequency at 30 and stop the inverter at 30 Hertz, Since my maximum frequency is 60, it'll go from 30 Hz to 0 Hz in 5 seconds. Because it had to go from the maximum frequency of 60 Hz to 0 Hz in 10 seconds. Since my frequency is halved, it must go from 30 Hz to 0 in 5 seconds. I'll start the inverter and set my DRV to 0 so I can do this through the keypad. I started the inverter. Now, if I stop the inverter, it will take 5 seconds for my electric motor to come to a halt. I stopped the inverter. It took 5 seconds for the inverter to stop. But the next stop mode is via DC. Braking, we go to parameter number AD8. We set AD8 to option 1. In AD14, we specify the duration that the inverter waits before applying DC current for the electric motor shaft to lock. We'll leave this set at 0. In AD15, we specify the duration for which the DC current will be injected into the motor winding. For example, I'll set it here to 4 seconds. 4 seconds. DC current is injected into the motor winding, and the motor shaft locks for 4 seconds. In AD15, in AD16, we also specify the percentage of the rated current we defined that the inverter should inject as DC into the winding. We'll set it to 50%. And in AD17, we specify the frequency at which the DC current is induced into the winding. For instance, if we set it here to 28, the inverter at 28 Hz and frequencies lower than 28 induces the DC current into the winding, and the electric motor shaft locks instantly. Okay, I'll go back. Now I'll start the inverter. Now, if I stop the inverter, as soon as the frequency reaches 28 Hz, the inverter injects DC current into the winding and the motor stops instantly. Now, I'll stop the inverter. As soon as it hit 28 Hz, it held the motor shaft for 4 seconds and my motor locked. Okay, the next stop mode is AD8 set to 2, which is via free run. In this mode, based on the load inertia on the electric motor shaft, the electric motor begins to come to a stop. Right now, my load inertia is low, so my motor should stop more quickly. I'll start the inverter. I'll stop it again. You see, because my load inertia was low, my motor stopped faster. So in the last option, depending on your load inertia, then after the stop command, your electric motor will begin to stop.